So this was one of the first instantiation of the work that two of my PhD students did, Abudi Kwadier and Eugene Vinitsky. And essentially, they started to do penetration studies of, the question is, how many cars would you need to smooth traffic, and how much energy savings would you produce with that percentage of cars? So these were the first penetration studies we run. Obviously, very idealized case, simple merge scenarios, but it was very interesting, and it did catch some attention initially. It was even picked up by Science magazine, so we're pretty excited at the time. Now, what we're doing today is we are trying to see if the same things I just described here could be applied to stop and go waves. So stop and go waves, known as jammetons, phantom jams, etc., are essentially waves that happen, like you see here, for no good reason. It's just this same human inability to self-regulate that leads to these instabilities. So technically, the demand is not high enough to fully clog the freeway, yet it reaches past jam density in geospatially varying locations that depend on the instability. So the idea is, could you use that to smooth these waves? So when we do that, now we look at real scenarios. And so typically, the models that we use for this are micro simulations that are generated by the Connected Corridors teams in California. So these are working for District 7. So these are fairly, sophisticated micro simulation runs that also includes arterials. We mostly apply it for the freeways. That we used for the training of our models. So the same thing that I just showed you in Sumo, this one is in IMSON, but we're going to use now to train our model in software. More specifically, what you see here is essentially the waves. So I'm going to just pause and explain. This is a zoom of the previous. This one is on Sumo. The traffic goes eastbound. Initially, it has white cars, so just like IDMs. It has a few red cars, but they're not on. They just behave like humans. And initially, you're going to see these waves happening in that calibrated model. Ultimately, some cars will turn in blue. That means now we turn on the autopilot, and that will hopefully smooth the waves. So that's what you should do. I know that's not great to see over Zoom because it's a little bit complicated to show movies at high frequency over Zoom, but hopefully you'll see that. So right now you see that big wave forming here. It's getting into the box right there. So you can see now it's in the box. And now you have these waves that's going back and forth, back and forth. You might not be able to see this through the Zoom, but I'll tell you it's go back and forth and back and forth. And there's no controller. In about 10 seconds, you're going to see the controller being turned on. When that happens, there's blue cars or cars that will be turned in blue. These are the cars that can be sensed by the automated vehicles, and it will try to flush the oscillation. So right now, everything is clogged. There's these waves that are back and forth and back and forth. Now you see the blue cars. So that means now the controller has been turned on and it's starting to smooth things. So you might be able to see it through your screen. The flows are getting smoother. The waves are being damped. And even though we're slightly above critical densities now, there's no more oscillations. And the more I let it play, the more you'll see it flushes things. And that's the aspiration we have here with these algorithms. So essentially, we're trying to smooth things. We're not looking at improving travel time, and we're not looking at changing VMT either. The idea is you work with fixed VMT, nearly fixed travel time, but you smooth traffic, so you prevent the stop and go while maintaining the throughput. That's kind of the illustration of what I just showed you. So essentially, without the control policies, you have, so this is a 4-lane freeways, you have all the shock waves that happened. With the real, the RL control policy, I mean, you still have congestion because that's not going to change, but you notice that this is more on the yellow side and there's no stripes of red, which means essentially you've managed to smooth the waves. And so the question is, when you do that, how do you do that? And you have to be careful because so the idea is you would like to reward the energy consumed and say, well, the more energy you save, well, the better you do. But there's a very trivial solution, which is, okay, stop all the vehicles and then you get a zero energy, and that's optimal. And that's true. But of course, that's not what you want to do. So when you start to shape a reward for an RL algorithm, there's a lot of work to be done in understanding how you're also going to integrate the constraints. Like, for example, how do you maintain the constant throughput? or how do you make sure the vehicles don't stop? And so in order to make these algorithms work, in fact, there's a lot of kind of experimental algorithmic design that is needed. There's not much theory, but it's just more, how do you devise a reward function that will not produce some kind of stupid behavior where to achieve optimality, you stop all the vehicles.